Well, good morning, everyone, and welcome to today's CAR seminar. My name's Josh, and I'll be facilitating our session. Today's seminar will be presented by Dr. Alexandra Larsen. The presentation is on a deep learning approach to identify smoke plumes in satellite imagery. Dr. Larsen is a statistician in the Chemical and Pollutant Assessment Division of the US EPA, and her research interests lie in the intersection of the environment and human health. So today's presentation will be recorded and made available online, and we will have a session for questions at the end. So please feel free to enter questions into the chat during the presentation or at the end, and I will present them to Alex following her presentation. So to get us started, I will invite Dr. Larsen to begin her presentation.
Great, thank you, Josh. And thanks for the invitation to speak today. And thanks to all of you for tuning in. Go ahead and get started here. So as Josh mentioned, today I'm going to be talking about a deep learning approach to identifying smoke plumes in satellite imagery for health risk communication. And the reason why we're focusing on wildfire smoke in particular is because of its of how it's emerging as a key issue in public health. Wildfire smoke contains numerous hazardous gases and particles, and its exposure is linked to detrimental health outcomes. There's a lot of literature linking smoke exposure to aggravating respiratory diseases, but there's also a growing body of literature linking smoke exposure to cardiovascular disease as well. And overall, some studies have shown that air pollution from wildfires contribute to tens of thousands of deaths annually around the globe. So this is not an issue that's localized in any way, and wildfires are increasing in frequency and severity again across the globe. And the images that we have here are the major wildfires that struck Australia. Those are the two images on the left, top and bottom, and the two on the right are satellite images of the very devastating wildfires from the west coast of the US. So this is an important issue, and so it's also important to effectively look at tools for effectively managing smoke-related health and air quality impacts. So that's what I'll be talking about a bit today. So one way we can mitigate the negative health effects of wildfire smoke exposure is to have state-of-the-art communication tools. And what I mean by that is the ability to track the location and the extent of smoke plumes and communicate that information in near real time. And that's important because smoke can travel vast distances. It's not localized to the hot spots where the wildfire episodes are happening, and we can actually see health effects far away from fire centers. So it's important to have information not only of where the fire is, but also where the smoke is going. And this is important for the entire population of people who are near fires. Rural areas have sensitive agriculture, and in addition, they may not have local means for smoke detection. So widespread smoke detection tools are very important from that aspect. And then looking at urban areas that have denser populations, there's more people that we need to protect from the harmful effects of smoke exposure. And then of course, these kinds of tools are very important for fire managers and public health officials who are actively fighting fires and smoke effects as they come in. So current methods for smoke identification, usually air quality impacts from wildfires are assessed by a combination of different things. There's monitoring networks, simulated forecasts, and satellite imagery. And something that we have to sort of be careful about with the monitors is while they're high quality, they are usually sparsely distributed. So that can hamper our ability to track smoke at a high spatial resolution. But we have newer generation satellites are becoming really data-rich alternatives. The geostationary satellites can provide data at 10-minute intervals and at 1 to 2 kilometer resolutions. And there are some polar orbiting satellites that can take images at less than a meter of resolution. So really high spatial and temporal resolution data here. However, the technology for processing such high volume input is could use some improvement. The U.S. National Oceanic and Atmospheric Administration, or NOAA's hazard mapping system, is a really excellent product that is out now. It requires manual inspection of satellite imagery that comes in. And the figure on the right here actually shows some HMS identified smoke plume envelopes over the US during the fire episode back in 2008. So they actually have an analyst who manually goes through those images and outlines the plume envelopes. So it's very high quality data. And it's updated twice a day, but it's nowhere near, the near real time capability, to match the satellite, the volume of satellite imagery that is available. So with this project, we sort of looked at using artificial intelligence algorithms, since these are really tailored to processing big data. And this is something that the remote sensing community at large is turning to. In particular, we looked at developing a fully convolutional neural network, or FCN. This is a deep learning algorithm for semantic segmentation. So it learns how to classify the pixels in images as one sort or another by referring to a training set of ground truth data. And it is fast, and again, it's designed to process large amounts of data, and it does have the potential to be operational in near real time. So some of the images at the bottom are examples of applications that we've seen so far in the remote sensing community, and these are applications of the FCN algorithm in particular. On the far left, this is an example of road segmentation being performed. So this black and white image here you can kind of make out the roads going through, and the image in the middle with the green, this is the ground truth data. So someone has actually gone through and labeled each pixel in the image as either road or not road. And then the FCN trains on this ground truth image, and it's produced this representation here on the left, and done a pretty good job. And you can see that with weed mapping. This was an example of the application here, separating out identifying weeds from rice and rice farms. And this is our ground truth, and the algorithm has learned how to make that distinction, and this is a representation here. And then one more example of an application for sea and land segmentation. So we noticed that this algorithm was successful in other applications for processing satellite imagery. And the idea is to apply it to smoke identification. So what I'll be talking about today is a proof of concept that these FCN algorithms can be developed to identify smoke plumes in new generation satellite imagery. And we use the output from currently operational methods for smoke identification as the ground truth training data. And there's a couple of benefits to this approach in particular. So we're leveraging current and validated smoke identification products by using these products to train the algorithm. We're sort of taking advantage of all of the science and knowledge that has gone into the problem of smoke identification in satellite imagery. And by incorporating that into a machine learning framework, we have the potential to operationalize the system to be operational in near real time. And we're also taking advantage of the vast amount of data that's coming in from new generation satellites. So we demonstrate this for a fire in the Northern Territory of Australia. But the goal and the hope is that the algorithm can be trained further so that it can be applicable to any geographic region that's being impacted by smoke. And this information is something that could be used by fire managers and health and environmental agencies, and as well as the general public, to better manage the health risks associated with fire smoke exposure. So I'll talk a bit about the network we developed, starting with the data that we input. We're of course using satellite imagery, and this is from the advanced Himawari imager on the Himawari 8 satellite, which records data at a 2-kilometer resolution in 10-minute intervals. And we used 6 spectral bands, the RGB bands from the visible spectra, near infrared, shortwave infrared, as well as top of atmospheric temperature. And we also included fire radiative power of burn hotspots to help the algorithm distinguish between cloud and smoke, which is a pretty typical issue when doing smoke identification in satellite imagery. And so these are hotspots that are detected twice a day at a 375-meter resolution from the NOAA VIIRS satellite. And the ground truth data, as I mentioned, we wanted to use data that was from a current and validated smoke detection product, and this is one of them. And again, what we mean by ground truth data is the data that we'll use to train the machine learning algorithm to identify smoke and within the input images. And we have so the data looks like for each pixel there's a label of smoke or not smoke, and the goal is for the algorithm to be able to distinguish which ones are the smoke pixels and which ones are the non-smoke pixels. And so our ground truth data comes from analytically derived aerosol types, and this is a method developed by Ken and his lab, and they published a paper on this in 2019. And the sort of general overview of the process, they take imagery from the Himawari 8 satellite and conduct cloud masking, and then calculates aerosol optical depth fields to estimate various aerosol types, including smoke. And this is on a 2x2 kilometer grid in 10-minute increments. And the image on the right here is the study area in the Northern Territory. And we have the pixels. You can see sort of this gray area coming from the burn, that's the smoke, and the black pixels are the smoke labels from the analytically derived, from the analytic method. So this is what we're, an example of one of the images that we're using as the ground truth. And so this is an overview of the FCN for smoke detection, just an overview of the whole process. So we'll start with our input images from the Himawari 8 satellite. And these are unlabeled, so we don't know whether each pixel is cloud or smoke or something else. And then the neural network takes the images and makes a guess of the classification for each pixel, and then compares that guess to our ground truth images where we know the labels of smoke and non-smoke, and then updates the parameters within the network to make sure that its guess is close to the ground truth, and iteratively repeats this process until there's an acceptable amount of difference between its prediction and the ground truth images. And then we have a network that we can apply to new data from Himawari 8 or other satellites and other geographic regions. That data could be fed into our trained network and produce pixel-wise classification in near real time. So I'll go into the details a little bit for the model itself, and before jumping in, I'll talk a little bit about the terminology I'll be using. And so just again, the FCN is a neural network. It's a model that relates inputs in the form of satellite imagery to the ground truth. And the model consists of a series of operations. And in machine learning, we refer to those operations as layers. The output of each layer becomes the input for the next layer. The number of layers defines the depth of the algorithm. So we talk about deep learning algorithms. These are algorithms that have several layers to them and several layers of operations being performed on the input data. We sort of organize the layers into blocks, and I'll be talking about these a little bit more. The first one is an encoding block that performs downsampling, and you can sort of see what that looks like. This image at the bottom here shows the dimensions of output from each operation. So these are the layers of the network. And we take some input image and then downsample, so bring it down to a low resolution where we have more information, like the very distilled information from the input images. And then you have the decoding block, which is the second half of the network, which upsamples and basically projects the lower dimensional representation back to the original dimensions. And then you get a prediction layer at the end, which categorizes the pixels into different categories. So talking a little bit more about the encoding block, again, this is a group of operations that discern local features in the images that are indicative of smoke plumes. And it consists of a few downsampling operations. And we use convolution, which is essentially a parametric kernel smoothing. And this top image here illustrates how convolution kind of works. You have your input image and a kernel on top, and you compute the dot product between the kernel or the filter and the input, and you get a single value. And you sort of slide and repeat to get the output here. And again, that conducts the sort of spatial smoothing of the input. We also used max pooling, which computes local spatial maxima. And that's illustrated here. So with this, you kind of, if you have a 2x2 filter or kernel that you're working with, it takes the maximum of the values within that 2x2, and we compute that across the entire image to get a smaller representation of the inputs, and it sort of records the most salient features. We also include a restricted linear union or ReLU function, which is nonlinear, and it adds has the added benefit for the network to be able to learn nonlinear relationships between the input and the target data or the ground truth data. And the result from the encoding block is a lower dimensional representation of the data. The decoding block projects the coarse output from the encoding block back to the original spatial scale. So we have transpose convolution is the primary upsampling operation, and it's illustrated here. You can see that's projecting and data back to a larger scale after convolution does the opposite. Also includes ReLU and batch normalization to stabilize the network, and skip connections is also an operation that allows stabilization as you go through. And finally, we have the prediction layer where we're classifying each pixel in the image as smoke or not smoke. And that involves another convolution and utilizes a sigmoid function to transform the predictions at each pixel to a scale of 0 to 1. And then we say that we classify each pixel as smoke if its value is greater than 0.5. And that's something we chose through sensitivity testing. So to train the model, we compare, the goal is to minimize the prediction error against the target data set. And we used a stochastic batch gradient descent to optimize the model parameters with respect to a binary cross entropy loss function. This is something that you can choose for your network, but this is commonly used for object segmentation. And the parameters that are being learned are involved in the convolution and transpose convolution layers of the algorithm. The rest of the functions that we talked about are actually non-parametric. So it's just the parameters for convolution and transpose convolution. And we chose to run the model for 20 train and test cycles, which we call epochs. And each time we train on 70% of close to 1,000 images that we had in the data set. We evaluated the model on a 30% holdout set. And we randomly assigned images to either the train or the test set. So we compared to evaluate the model performance, we compared to logistic regression, which would be sort of maybe a naive approach to evaluating the data. In that we have the ground truth as the response, and we included the spectral bands and hotspots as predictors, and used five-fold cross-validation to calculate performance metrics, and those include classification accuracy. So we looked at the percentage of correctly classified pixels out of the total. We looked at intersection over union, which evaluates the precision, looking at the overlap between prediction and ground truth. And we also looked at IOUs, or intersection over union, for the true positive and the true negative. So by true positive, we're looking at the smoke and true negative, we're looking at the non-smoke pixels. And in many cases for these images, we have a much larger proportion of non-smoke pixels to smoke pixels. And so we had to try to account for that imbalance. And in doing that, we report a weighted true positive and true negative IOU, and that weight is based off of the number of smoke or non-smoke pixels. And we'll kind of get to that later on and see the importance there. So briefly, just to summarize, this is the model that we came up with at the end. We had 6 encoding layers and 6 decoding layers. And we went pretty fast. This was on just a personal laptop, but went pretty fast to process our images. So the figure here just shows the input going through all of the operations and the dimensions of the output and getting us back to our prediction here at the end. Okay, so taking a look at the performance of the algorithm, it did outperform logistic regression, which was somewhat expected since the FCN takes into account spatial information from the images, where logistic regression does not. So you can see in all of the categories, accuracy, intersection over union, for overall, as well as the true positive and true negative, the FCN performs much better. If we look into these metrics for the FCN, we're seeing that it predicts non-smoke pixels better than smoke pixels. So if we look at comparing these two IOUs, we're really capturing non-smoke pixels extremely well, close to 100% of the time. But for the smoke pixels, this is a much lower number. When we weight this metric by the number of smoke pixels, that number goes up. But this is, we definitely see a difference in the model's ability to predict smoke pixels versus non-smoke pixels. And again, we attribute that to the fact that there's many more non-smoke pixels in these images than smoke. And just to really illustrate this, so this is our results for a large smoke plume. So an image where you have a lot of smoke pixels relatively. On the left, these are the model inputs, and the color scheme here, these are heat maps where red is 1 and blue is 0, and all of the images are normalized so that we can compare across. But in the RGB bands, you can see some signal. You can sort of make out a smoke plume. You can also kind of make it out in a temperature band, and we have a number of hot spots recorded here. And this image here, this last layer image in the model output, this is representative of what the neural network was able to kind of distinguish between. So it's saying that these red and orange areas are very different from the blue and green. So it was able to really pick out the smoke plume from the model inputs that we have. And when we do the prediction and sort of split these values into smoke and non-smoke, where this is the resulting image that we get, and we can see that it's very close to the ground truth, or the data from the analytically derived data. And then, looking at the performance for the large smoke plumes, we're getting close to 100% accuracy overall, good overlap overall, and drilling in and looking at overlap between for the smoke pixels. This is pretty high in the getting 70%, and then bumps up a little bit if we include the weight to 77%, and again, doing really well for the non-smoke pixels. However, if we look at a small smoke plume, we see a little bit of a different story. And this is such a small plume that there's not a whole lot of signal going on in the model inputs here. And the prediction ends up being a much smaller representation of what's actually going on. So, we do see really high accuracy for this, but the intersection of the union, so the overlap between the predicted and the ground truth pixels is much lower. And we see really low for the smoke pixels at 7.5%. However, that does jump up a lot when we include the weights. And we're seeing really good performance for the non-smoke pixels. And I think that's really driving accuracy here. So just kind of really drilling into the fact that we're getting high accuracy, for large smoke plumes and small smoke plumes, and even overall, if we're looking back here. But something that we'll have to kind of work on in the future is accounting for the imbalance between smoke and non-smoke pixels. Something else that we took a look at were some considerations for model retraining. So this is something that we imagine will be happening when if and when the algorithm is implemented at full scale. We need to be able to determine how often to retrain the network. And that's sort of a balancing act between having a sufficiently large training set to ensure good fit, and also being able to frequently retrain and allow the model to adapt to changing conditions and new data as it comes in. So what we did was we calculated our performance metrics over varying ratios of data in the train and the test set over 20 epochs. And what we found was that looks like you can retrain the model with a moderate amount of training data. And you can get acceptable metrics within a few epochs. So this is sort of promising information in that it indicates that we could retrain the network fairly quick, relatively quickly, which is important for getting to near real-time operability. And what we're seeing in the figures over here is, again, different ratios of the train to test set. So in this darker color, we only have 10% of the data in training. So this would train very quickly. And in the lighter colors, we have the opposite. We have most of the data in training. So this would go rather slowly. But what we're seeing pretty much across the board, I mean, just looking at loss here, and we want, loss to go down. This is a metric for the difference between the prediction and the ground truth. When you have just a little bit of training data, the loss does go down, but it takes a lot longer and it's slower, and it never gets as far down as you would if you use most of your data in the training set. However, if you look at sort of these middle ratios, middle colors here, they drop down a little bit slower, but they do get to the same level as the setup with data in the 90% in the training set. So this is how we're able to conclude that data sets with even 40 and 50% in training perform almost as well as data, putting 90% of the data in the training set. Okay, so some limitations. We do assume stationarity over time, which we think is reasonable for a very short study period, but can imagine how helpful it would be to incorporate temporal correlation in this model. We acknowledge that a fully operational model would require periodic refitting to account for seasonality and changes in the environment and technology that would go on. we didn't optimize the model performance with respect to some of the hyperparameters. We felt this was best suited for implementation and does require additional computer science expertise.
Hey, Brenda. Hi, sorry, I just was in a meeting, well, in a conference.
No problem. Thanks for joining us. So, so one of these, something that these limitations sort of highlight is a greater need and I think a good opportunity within the field of environmental equity to collaborate more with computer scientists in order to fully take advantage of deep learning for large-scale environmental data analysis. In addition, what we're hoping to do with this, going forward, if when it's operational, so the FCN model could be coupled with analytic algorithms, other analytic algorithms like the one we used to generate the target data, the ground truth data, and ultimately we want to develop this in near real time to be able to provide smoke plume envelope information for public health risk communication, automated alerts to fire control centers. And these smoke plume predictions, in addition to being useful for alert systems, could be used in conjunction with modeled and measured particulate data. I mentioned earlier with monitoring networks being sparse, that can be a bit of a limitation there, but using that data in conjunction with this would be helpful, as well as increasingly available data from dense, low-cost sensor networks. Can sort of couple those together and provide an integrated picture of smoke exposure across an airshed. And another potential future direction for this project is using the model to calibrate chemical transport models and again improve the ability to forecast smoke in near real time. So to sum up, we've talked about a proof of concept framework for automating smoke detection in near real time. We used a deep learning algorithm and a large volume of spatially and temporally resolved data streamed from a geostationary satellite. And we really took note of the fact that existing smoke detection approaches carry substantial scientific background and good performance. However, the computational burden related to processing high temporal data resolutions limits their capacity for real-time operational utility. So our goal here is to really bring all of these things together to produce a product for public health risk communication. And we feel the framework is relatively simple to deploy in the presence of current methods. And it shows promising results in terms of being able to detect smoke pixels in satellite imagery in an accurate and timely way. And this project would not have been possible without the folks on this slide. So the results of a collaboration between statisticians at NC State University and at the US EPA, as well as folks at the University of Sydney and Cicero and Duke University. So thank you all for your attention. I'd be more than happy to take questions now. If you have to hop off, there's my email address and I'd be happy to chat offline as well.
Thank you very much, Alex. It was a great presentation. It really seems like an exciting area with a huge potential. So I now invite everyone, if you have any questions, to enter them into the chat, and we'll use the remaining time to work through them. So to start us off, we've got a few questions from Jeremy Silva. So his first question is, can this method only obtain a classification, that is smoke versus non-smoke, or can you get quantitative measure of aerosol loading, for example, AOD?
Hi, Jeremy. Thanks for your question. That's a really, I think, a really interesting question. For this particular algorithm, the training data that we have is just smoke versus non-smoke. But I believe there would be other deep learning algorithms that could possibly learn something on a more continuous scale. So it's really a matter of what kind of data that you have to train with and what algorithm that you're using. I think for this particular algorithm, it's just geared towards the binary smoke versus non-smoke. But again, I would think it would be interesting to look into, others that could do continuous prediction on a continuous scale. That's a good question. Yeah, right. I can see that being very useful.
We have a second question from Jeremy. Is the fitting done independently for each pixel, or does it look at larger areas at once? If it's independent, do you expect much difference in performance as if it runs across areas simultaneously?
Yeah, I would definitely expect it to make a difference if we were going pixel by pixel. So the way this network works, and it actually does take information around each pixel. It does take spatial information into account. Something it doesn't take into account is temporal correlation, which I think would be a very big help. If you have smoke in at one time point, it's very likely that means there's smoke in the next time point. So that's something that we would very much like to expand on.
Okay, I think Alex, you may have addressed Jeremy's next question about using information about what pixels normally look like. So we might move on to his final question, which was, which of the input parameters were the most informative for the predictions?
That's a great question, and it's not something that we really looked into. Visual inspection seems like the temperature was really informative, and in some cases RGB. And I would imagine hotspots is also informative, but it's not something we looked into, and I think would be really useful to look into in the future. Yeah, that's a great question.
Thanks, Alex. Another question, this one is from John. Can any dimensional reduction pre-processing, for instance, principal component analysis or topographical data analysis, be useful?
I haven't seen PCA in particular being used, but I do think we did some pre-processing. We normalized values. I do think that can help. You have to be careful that you're not losing too much information when you do that. But I do think some pre-processing, can definitely be helpful in these cases.
Okay. We have two questions now about the training and the images. They're simulated, so I'll give you both at once. So the first is, how many images, can I ask how many images were trained in test and how long it's being used to train the model? And related to that, to address unbalanced training sets, would feeding an adjusted balance be useful, and then recalibrating back to the original probabilities be useful?
Okay, great. So to answer the first question, I think was about the number of images that we had and how we split those into the training test sets. And we had 975 images for this area. So we looked at a very small area and isolated one fire episode, and just looked at the time frame where there was smoke, and that resulted in about 1,000 images. And we split that 70 and 30%. So we trained on 70% of the data and tested on a 30% foldout. Does that answer that question there?
I think we'll wait a follow-up if there's any.
Sure, okay. And then the second question, Josh, would you mind
Sure.
repeating that?
No problem. So that was, I think, talking about the fact that there are so many more pixels with no smoke. So it's to address the unbalanced training sets, would feeding an adjusted balance be useful, and then recalibrating back to the original probabilities?
Yeah, this is an interesting question to me. I haven't looked into doing that myself. So I'm not, if I'm understanding the question correctly. So if you adjust the balance, I would be worried about distorting the images, but you might be able to kind of take that into account. Yeah, so this is a new method to me, but I think it would be worth looking into. I would be, I guess, if you were doing any kind of image distortion, would be careful about making sure that you could sort of undo that at the end, because you do want to make sure that if you have a plume, you're kind of keeping the integrity of that in the data set.
Thanks, Alex. So just wrangling some questions here. Another one that we've just had, have you noticed any effect of time or day on the remotely sensed images and the ability of the algorithm? So basically, does time of day affect performance?
I would imagine that it does, and I think there was definitely some discussion with our group of whether or not to include nighttime imagery, because that does look very different from daytime. So yes, I do think that has to be taken into account. I think it would make sense to even include that as a covariate if possible. So the algorithm knows, okay, operating at nighttime, things are going to look completely different than they do during the daytime. Not exactly sure, how to incorporate that, but yeah, that's definitely an important factor. Something to look so different.
Thanks. Another question from Yu Ming. So he says, thanks, Alex, great work. The model performance of logistic regression depends on the parameter setting for predictors. It cannot address the nonlinear and interactive effects automatically. Have you set the nonlinear and interaction function explicitly yourself?
So I might have a follow-up question here. So you say nonlinear function within the logistic regression or within the FCN? We do have nonlinear
Alex,
capabilities.
I think this is asking about the logistic regression and what functions inside that.
Mm-hmm. So we just used a very sort of vanilla logistic regression here, with a linear relationship between the predictors, the images, and the ground truth. So looking at each pixel with the data point there. So if you really wanted to use logistic regression to solve this problem, I think you would have to beef it up quite a bit to capture the relationships going on between the input images and the ground truth images. It's not necessarily a linear relationship there. Yeah, so that brings up a good point that you could be, like I said, beef up the logistic regression a little bit more and you could see some improvement there.
Okay. I might ask a few questions of my own at this point. So bearing in mind this is likely a naive suggestion, I noticed with the detection of the plumes when we compared both the large and small ones, it's much easier for the algorithm to detect higher intensities and also to detect the center of the plumes. Do you think it would be effective and reliable to say add some sort of buffer around what the neural network has identified?
I think that you bring up a really good point, Josh, that we did have decreased performance around the edges of the plume. And so I think at one point we did sort of look at, what can we do? What can we do there? Whether adding some kind of buffer, or doing our own smoothing beforehand to really sort of bring those border pixels in. Because that was definitely an issue. Is the prediction with the border pixels. So I think that adding some kind of buffer or doing some kind of smoothing would most likely help with the predictions. Yeah.
Thanks. Another question. This is focused on the generalizability to, say, other areas. So the testing so far has all been done, I think, over the Northern Territory on quite a consistent background. So it mostly looked like desert. There weren't a lot of irregular patterns. How would you expect performance to be affected by running this, say, over a forest or over a city?
Yeah, I think that we would it would be expecting a lot of this network that's trained on such a nice, easy area to perform just as well over an urban area, or as you said, over a forest, or even something that has something on the coast where you have the ocean kind of maybe getting into the image as well. So I think to mitigate those issues would require training in those specific areas. So looking at fires that are happening in different areas, and then perhaps finding a way to kind of bring those together. You may have to include some data on land cover. We just did smoke versus non-smoke, but if you had data on land coverage as well, that might help the algorithm be able to distinguish, because you bring up a good point. This works for our, again, nice clean area in Northern Territory where we focused, but in order to make it operational on a large scale, it would require training with a lot of different geographies to make that happen.
Thanks, Alex. We have a follow-up question on the same topic. So this is asking, would new models need to be built for different locations? And related to that, is AUC a useful metric for this type of work?
Yeah, it is. And we, at one point, we were looking at AUC. I'm not sure I could remember. We got a pretty good AUC for the FC, and it's better than our logistic regression in this case. So yeah, that would help. That does help with the training to be able to keep an eye on that metric, definitely. And yes, I think in order for it to be able to expand, they would have to be trained in multiple areas. And this is typical for machine learning. It can only do what what it's trained. So if you don't teach it what a tree looks like, it's not going to know. So yeah, this is kind of part of the process with developing a large scale machine learning algorithm that works for a large geographic region. We require training so that it can, you know, operate just as well in an urban area.
Thanks, Alex. I think we might finish with one last question, and that's from Pushan. And they ask, are these algorithms or products available or will be available for other users?
Yeah, so the hope is that they will. And I think this is becoming a more active area, this application of these deep learning algorithms to these kinds of areas. I'm not aware of any as of yet, but I do know that it's an active area, and the hope is that will you know, this will be developed as something that can help with, you know, near real time alerts going forward.
Thank you. So I think we're nearing the end of our seminar today. So I'd like to thank everyone for joining us today. In particular, on behalf of CAR, I'd like to thank Dr. Larsen for her presentation. So that brings us to the end of today's seminar, and I'd like to wish everyone a good day, and a recording of this presentation will be made available online. So thank you, everyone. And thank you, Alex, again.
Thank you, everyone. Thanks, Josh.